Hello students, in this video we'll discuss the algebraic value of the covariant derivative. Let's be given a vector field on the surface S, and we can parameterize this by R of u and v. Then W of t, our vector field, is really A of t R u plus B of t R v, like that. Okay, excellent. And so now if I differentiate this, if I look at W prime of t, that's going to be A prime of t Ru plus B prime of t Rv plus A of t, and then RUU times u prime plus RUV v prime, and then plus B of t times RVU u prime plus RVV v prime, like that. Beautiful. Okay. Now I can expand out these things. I'm going to look at the coefficient of RU, for example, right? And so I know, what can we say? We can say that RUU, we'll call that RUU, is really what? RUU is really gamma 1, 1, 1, gamma 1, 1, 1 RU plus gamma 2, of course, 2, 1, 1 RV plus L n hat. I know that RUV is equal to what? Is equal to gamma 1, 2, 1 Ru plus gamma 1, 2, 2 Rv plus M n hat. And then RVV is going to be gamma 2, 2, 1 Ru plus gamma 2, 2, 2 Rv plus n hat, like that. Beautiful. Okay, we have these three things. And so now what I'm going to do is I'm going to look at the terms in this derivative of this vector field that do not contain the normal vector, right? So I'm going to define dw dt, like this, the covariant derivative. And it's going to be what? It's going to be all the terms that come from RU. So let's look at the terms that have RUs in them. So this term over here is an RU. So we're going to have A prime of t. That's going to be an RU term. That's an RV term. Now over here, we're going to have an A of t. And then this term, well, how does this term contribute to the RU? So this term over here contributes to the RU like a gamma 1, 1. So I'm going to have an A, a U prime, and a gamma 1, 1. So I have an A, U prime, and then a gamma 1, 1, 1. That's going to give me an RU term. This term over here is going to give me an RU term. It's going to be an A, and then a gamma 1, 2. So A, then that's going to be an A, then a V prime, then a gamma of what? Then a gamma 1, 2, 1, 1, 2, 1. This term over here, I have a B, and then a gamma 1, 2, 1 U prime, a B plus B, and then a U prime, and then a gamma 1, 2, and then over here that's going to be a gamma 1, 2, 1. And then finally this last term is a gamma 2, 2, 2, 1 plus gamma 2, 2, 1. And then what's that hit with? That is hit with a V prime and a B. B, V prime. So those are my RU terms over here. So these terms are multiplied by RU, so let's give ourselves a little more space. So these terms are the coefficient of RU. So we're going to define this. Define dw dt to be RU, and then plus RV, and then what terms are left over? So the RV terms are going to come from what? A B prime of t. Then I need to get all of the terms that have an RV in them, so this is going to be a gamma 1, 1, 2, so I'm an A u prime, and then a gamma 1, 1, 2 will come from this term. This term is going to be an a v prime, so an a and then a v prime. And then over here, this is going to be a gamma 1, 2, 2. Gamma 1, 2, 2. Plus what? Plus, over here, we're going to have a bu prime, and then a gamma what? Then a gamma of 1, 2, 2. 1, 2, 2. And then plus what? The last term over here is going to be a b v prime, gamma, and then 2, 2, 2, like that. And so this expression over here, so dw dt, is the covariant derivative of w. That vector field. Okay? Beautiful. Now, what do we want to do with this thing over here? We want to figure out how we can express this, find this expression. And so here's a proposition. Let's suppose that w hat of t is a unit vector field. Then dw dt is equal to some number lambda over here times n hat cross w hat, like that. Okay? Okay? Good. And this value lambda over here, so lambda is the algebraic value of the covariant derivative. Covariant derivative. Beautiful. Okay. Now, how do we find this lambda over here? Well, I can find lambda by dotting this covariant derivative with n that this, right? So what can we say about this now? We can say that dw dt dot product with what? Dot product with n cross w is equal to lambda, right? Okay. And furthermore, what do we know? We know that this thing over here, this dw dt, is really w prime minus n. So since dw dt is w prime of t, and this is a unit vector in this case, minus some constant, let's call it sigma n hat, right? Some number that's in the normal direction, right? And so, of course, if I dot this normal vector over, if I dot this component over here with this n hat, that's going to give me 0. So, in other words, lambda is equal to what? This lambda is equal to the inner product, w hat prime, dot product, what? Dot product with n hat cross w hat. And that gives me a formula, the triple scalar product over here of w prime, and n up to sign gives me the algebraic value of this covariant derivative. Now, in particular, there's a special case of this. And what's that special case? If w is gamma prime, so if w hat is gamma dot, arc length parameter for a curve, here's our example, then what's this lambda going to be? Then lambda is going to be gamma double dot, dot product what? Dot product n hat cross gamma dot, and that's exactly what? Well, this is exactly just the geodesic torsion, the geodesic curvature of the curve. So this is kappa g, geodesic curvature. So in particular, what can we say about this thing? We can say if the algebraic value of the velocity field, or if the algebraic value of the velocity of a curve in an arc length parameter is equal to 0, then that curve is a geodesic. So that ties together this notion of algebraic value of the covariant derivative with the idea of a geodesic. We'll explore in further videos how this algebraic value relates to the angle in between two unit vector fields. Thank you very much.